Good evening. So it is 6 o'clock on Tuesday, the 5th of October. So it is time for our live tuition session. Physics with Keith, under the stairs, somewhere in the south of Essex. Oh, hello, Lex. Good to see you there. So this is your first time tuning in. The way this works, I hope this is okay. I've got the microphone in a slightly different position today, so hopefully you can hear me okay. Let me know in the chat that way if you can't. If this is your first time tuning in, this is how it works. So I'm broadcasting on YouTube, but people can participate by putting something in the chat that they can see to the left there. That's good. Thanks. Thank you, Edward. That chat is found on Discord, and the link to the Discord channel and to the Discord server is below in the description of this YouTube video. Of course, if you're on Discord already, then you can see and you can interact, and that's great. If it's your first time joining in, then you'll need to request to become a participant. I do that as a troll stopping mechanism. Essentially, if you go onto a particular channel, the instructions are on this Discord server. You go onto a particular channel called Request to Join and just drop a few basic details there, nothing too private. Then I'll switch your account so that you can participate, join in, send messages, just like Lex, Edward, and 𝗟𝗪𝗀𝘀𝘀 have done, and 𝘭𝘪𝘀 and 𝗵𝗵𝘀𝗀 and 𝗵𝗛𝗡 and 𝘭𝘪𝘯𝑀 and everyone else that I've missed, and I'm very sorry if I have. So this is the last session, I think, in our series all about nuclear physics. In this session, we're going to be looking at nuclear energy. In the previous sessions, we have looked at radioactive decay chains, nuclear decay chains. That was the first one of this series. Then we had a look at half-life. Then we looked at penetrating power. And so now we're looking at nuclear energy. The way I structure these sessions, the first half of the session, roughly half of the session, will be GCSE level stuff. And the second half will veer into more A-level stuff. And I encourage students who are studying physics at GCSE level to persist into the A-level stuff. Whilst you won't be examined on it at GCSE, it's all good physics. And that's what it's all about, good physics, not just passing exams. I have also assigned another homework task on Isaac physics, and I'll tell you more about that at the end. So, should we get on with it? Let's get on with some nuclear physics. Yeah, let's do it. Nuclear physics. Woo! Okay, so nuclear fission reactions. That's what we're talking about today. We'll talk a little bit about nuclear fusion reactions as well. But mostly the main bulk of what we talk about today is going to be nuclear fission reactions. So you can see I've got some pictures here which are Creative Commons licensed, and therefore I'm free to use them. These pictures I've stolen straight off Wikipedia to try to make some points. First of all, if I have a uranium nucleus and a neutron is absorbed by that uranium nucleus, it becomes unstable. I mean, it's already unstable, but it's got a pretty long half-life. It becomes an isotope of uranium that is much less stable, a much shorter half-life. And that will very quickly decay. Now, for the first lie that you may get told. In GCSE level, you may get told that it decays by fission, splitting into two equal size fragments. Well, that's not true. You may have been told that it splits into 1/3, 2/3. That's not quite true either, although it's closer to the truth than splitting into equal daughters, equal fragments. No, what actually happens is you get a probability, a chance of the different sizes. And so stolen off Wikipedia is this graph on the right, and there's lots going on here. But if you just look at U235, that's the red part, you see there's a peak around here, and there's a peak around here. What you're looking at is the atomic mass of the daughters, of the fission products of uranium-235 fission. If you look at the green one, you're looking at the less common uranium-233. You look at the blue one, you're looking at plutonium-239, and so on. But you can see that they overlap quite a lot. You sort of get around about 135 and about 95 as the masses, but there's some sort of range to it, and it's all based on probability. So that is the first thing that I'm going to tell you, which is also, funny enough, a lie. Because it turns out that it is possible to get nuclear fission that produces 3 daughters. It's not very likely. It's something like 2 in 1,000 nuclear fissions, but it's still significant enough with how many nuclear fissions are happening that you're going to get daughters with much smaller atomic masses than these forming within the reactor core. So that's the first thing I thought would be fun to talk about. You'll also get told fun lies like you always get 3 neutrons or 2 or 3 neutrons that are released in this process. It could be different numbers. It's not always as cut and dry as that. So there we go. That's an introduction. Dead easy. So what do we need to do? We need to get one of these neutrons that's released to cause a fission reaction in another uranium-235 nuclei, and so on, and nucleus, singular, and so on, and so on, and so on, and so on. And so that's the idea of getting a chain reaction. I'm going through this very, very quickly, mainly because this stuff, although it's interesting and stuff, it's not what I want to spend most of today looking at. So if I scroll down a little bit, you'll see the old classic picture. It's not animated, I'm afraid. If at any point you've got questions, chuck them in the chat. No one knows you. It's fine. Chuck them in the chat. Any point you've got questions, say, whoa, 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 that was too fast. Chuck them in the chat. Because I'm using a lot of technical language and things. So Jamie says, nuclear fission, the energy released, and also what are the daughters? So these are good questions. So nuclear fission is the process by which a large unstable nucleus splits into 2 more stable nuclei, or more, could be 3. It doesn't have to be binary fission. So it can split into 2, or very rarely 2 in 1,000, something like that, fission, split into 3 of these products. Daughter is just what we call the products of nuclear reactions. We call them daughters. So alpha decay, for example, which we've looked at in the previous week, we have an unstable nucleus that will decay via alpha decay. The product of that is called the daughter isotope. And I suppose you could have granddaughter and so on if you have that daughter isotope also unstable and then decaying as well. So that's what I mean by daughters, fission products. This picture, again, straight from Wikipedia, Creative Commons. You can't see anything about nuclear physics without this picture appearing. Anyone happen to know what type of nuclear reactor this is a picture of? Anyone happen to know? It is a nuclear reactor found in a power station. That's true, Jamie. There are nuclear reactors that are not used in power stations, so that's a distinction that is worth making. For example, nuclear reactors can be used to breed, that's the terminology we use, to breed other isotopes, and some of them can be used for nuclear medicine, for example. But Pranav is correct here. This is a pressure water reactor. It's very similar to a boiling water reactor, Helicopter Boy, but not quite. So this is a pressure water reactor. The differences are subtle, but it's all to do with the pressure that the water is kept under and the temperature that the core will reach. So let's go into this reactor, not literally, obviously, that would be unsafe, but let's go into this reactor and see if we can pick apart what the different parts are and what they do. Now, if you've never studied nuclear physics before, nuclear reactors before, then this is going to be very new to you. And that's okay, because in the chat below, you'll see that other people have studied it before and they'll be able to offer answers as well. If you have any questions, you must ask. So the first thing, the most important part inside this reactor, you would not have a nuclear reactor without it, is the fuel. Anyone happen to know what element we tend to use in commercial nuclear reactors found in power stations as a fuel? It is indeed uranium, so it looks like everyone bang, 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 bang with the answer. Absolutely. That's not the only fuel. There are developments in thorium breeder reactors which have certain advantages. One advantage is that they don't produce plutonium. Krypton? No, I wouldn't say so. Not that I'm aware of, Jammy, but I could be wrong. Not that I'm aware of. No, uranium. Plutonium as well is a nuclear fission fuel. But plutonium does not naturally occur. Not in the. You don't dig up a nice vein of plutonium ore in the earth. We do. We can dig up uranium ore, just like we can dig up iron ore or copper ore, but we can't dig up plutonium ore. Anyone know why? Why can't we dig up plutonium ore? Helicopter Boy, you are correct, but several things. Firstly, no one said that this is going to be at atmospheric pressure. And secondly, the fact that it's a gas doesn't mean it can't undergo nuclear fusion, or sorry, nuclear fission. But I don't think so. I think krypton is too light a nucleus for that. Yeah, Dvorak, but why? That's the question. Sorry, I shouldn't be drinking while I'm talking to people. Pranav says, short half-life. So most of the plutonium's gone already. Yeah, not just most of it, almost all of it. There's trace amounts. So plutonium has a much shorter half-life than uranium. So it just doesn't stick around as long. Now, the plutonium that we have on Earth, we do have plutonium. We've got lots of plutonium. In certain places in the world, you can find big stockpiles of plutonium. Anyone think of where a stockpile of plutonium might be? I have to say that with a certain amount of disdain, I'm afraid. Stockpiles of plutonium. Anyone know where you might find a stockpile of plutonium? You can go with places, Jammy, or you could be more vague than that. So, Helicopter Boys, yeah, Jammy, there will be some in Chernobyl. There will be some, but not a huge stockpile of it. So, Pranav and Helicopter Boy are on the right lines. February spelt wrong. Actually, not so much. Edward, we do have plenty in this country, but nowhere near as much as the USA or the or Russia. Yeah, not so much, James. Not so much nuclear waste. And the reason why plutonium doesn't tend to find its way into nuclear waste is because that's part of the reason why we have nuclear reactors. A big part of the reason. Plutonium is easier to fission. It's easy to fission. Sorry, not easier to fission. It's easy to fission, and it's easier to separate chemically from isotopes of uranium that are harder to fission because plutonium's a different element. So we make plutonium as a waste product in nuclear reactors. The plutonium does undergo nuclear fission, but it's a byproduct of fissioning uranium or neutron absorption of uranium-238. It will decay into plutonium. And that's why nuclear reactors existed right from the 1950s. That's why they were made. To make plutonium so that we could make bombs. So the biggest stockpile of plutonium, I'm sad to say, are weapons compounds in the nuclear states. For example, the United States of America, Russia, the United Kingdom. There are other countries that have nuclear weapons. India has nuclear weapons. China, I believe Pakistan, I'm not sure. Australia has nuclear weapons. France has nuclear weapons. Germany, I think, does. And so on and so on. Israel, we think, has nuclear weapons, although it's not confirmed. North Korea, I think, is debatable at the moment. Yeah, I'm not sure whether they do or not. They have the capability to launch nuclear weapons, but I'm not sure that's the same thing as having nuclear weapons. They have the delivery mechanism, but I'm not sure they have the weapons themselves. It depends on the bomb, Jammy, and there was a ban on nuclear weapons testing in the, I think, 1970s. But nuclear weapons technology continued to be, yeah, exactly, Helicopter Boy. So nuclear weapons technology continued to be developed, but there was a ban, an international ban on actually testing the nuclear weapons. So I think the bottom line is we're not sure, but they would destroy not just a city, you know, pick a city, I don't know, Cardiff's a city, isn't it? But it would, all of the suburb region around it, essentially a county. Then beyond that, you're going to have severe damage and devastation. Beyond that, you're going to have the medium-term effects of radiation sickness. It will, yeah. Pranav, you could be correct. I don't know. But essentially, a nuclear weapon going off in a city can not just devastate that city, but it will devastate the whole country and beyond. It would be, if I'm allowed to quote an REM song, the end of the world as we know it. Yeah. Yeah, 50 to 58 million tons of TNT equivalent. It's mind-boggling to imagine the destructive power of these weapons. Yeah, exactly. It's pretty unpleasant. So let's get back to nuclear reactors used for the generation of electrical power. Let's go back to nuclear power stations. So we've got the fuel, and it's mostly uranium. There's different isotopes, and we'll come to that later. That fuel will then undergo the process here. Of course, we need to have some isotopes near the fuel or within the fuel that are neutron-rich emitters of neutrons, but that's fine. We've got those. We can get those from neutron activation of other elements. So we've got neutron emitters that start the process off. But the process itself in modern reactors is designed to be very difficult to sustain. So neutrons, when a uranium-238 nucleus absorbs a neutron, it does not automatically fission. In order for uranium-238 to fission, it has to have a very fast neutron that it absorbs. So we slow the neutrons down. And if we slow the neutrons down, rather than uranium-238 fissioning, uranium-238 turns into uranium-239, that then decays into plutonium-239. There's two stages to that, but it decays into plutonium. So we design our nuclear reactor with uranium-238 that acts like brakes, slowing down that reaction by absorbing neutrons, the slow neutrons, without actually fissioning. Now, fast neutrons would fission uranium-238. So we have to slow those neutrons down. So within this nuclear reactor core here, there is something called a moderator. And the moderator slows neutrons down. Can anyone remember a typical element that's used as a moderator? There are lots of them, moderating elements. Carbon was used in the very early nuclear reactors as a moderator. Boron, not so much. Yeah. Boron, not so much. Boron does something else in a reactor, and we'll come to that. Water, yeah, Helicopter Boy, water is very common. So in a pressure water reactor, exactly, Gnome, yeah. So in a pressure water reactor like this one, water slows down the neutrons. And the way that happens is a neutron collides with a water molecule and exchanges some energy. The water molecule moves a bit faster. the neutron moves a bit slower. Yeah, graphite, exactly, Jamie. Graphite, carbon, graphite, absolutely right. So it takes around about 50 collisions before the neutrons are slow enough then to be absorbed by uranium-235, a different isotope of uranium. And uranium-235 will fission with slow-moving neutrons. It won't absorb fast-moving neutrons, but it will absorb slow-moving neutrons. Now, part of the reason for this is actually fiendishly complicated because it's to do with nuclear energy levels. And so I don't really want to get into that. Yeah, so Helicopter Boy, heavy water contains deuterium, like Dvorak says, an isotope of hydrogen. Water is H2O. If those hydrogen atoms, the nuclei of them, contains extra neutrons, like deuterium or even tritium, then the water is heavy water. So that's what the moderator does. Inside the core, you've got a certain proportion of uranium-235 and a certain proportion of uranium-238. The uranium-238 will fission with fast neutrons, so we slow the neutrons down. That's what the moderator does. Uranium-235 will fission with slow neutrons, so we make sure we got the right proportion of uranium-235 to uranium-238, so that we are absorbing some neutrons with the uranium-238, but still leaving enough to fission the uranium-235, which is the whole point of the reactor, to fission. Well, sort of. You can't get more neutrons without the fission, so the fission's important. So you've got to get the balance right of those two. So that's what the moderator does. You can design a nuclear reactor that uses fast neutrons, and you don't have to worry about slowing the neutrons down. But that's more difficult to control. So let's move on to the third component to the reactor core. We've spoken about the fuel, uranium, uranium-238, and uranium-235. About 98% uranium-238, about 2% uranium-235. We've spoken about that. We've spoken about the moderator that slows those neutrons down so that they're absorbed by the uranium-238. They are also absorbed by uranium-235, which fissions, but when they're absorbed by uranium-238, they don't fission the uranium-238, so it breeds plutonium, which is the point of the reactor. Disgustingly. My opinion may be coming out here too much. So what's the third component in a reactor core? The third important thing. Hey, Wombat's here. I didn't think you were going to make it. Good to see you, Wombat. Yeah, so coolant or control rods. We'll go with control rods and we'll come to the coolant in a second. So the third important thing, the control rods. If we were trying to control the reaction rate inside our nuclear reactor with the proportion of uranium-238 and uranium-235 alone, then it would be exceedingly difficult to control. We wouldn't be able to. I'm glad you could make it, Wombat. So instead, we have another mechanism called the control rod. And we have the reactor designed so that it's too many neutrons are buzzing around inside it. The neutrons that are buzzing around are produced when the uranium-235 fissions. When the uranium-235 fissions, neutrons are released. Those neutrons are going too fast. They're fast neutrons, but we slow them down with the moderator. But still, it's designed to have too many of these neutrons. So we can take some out. And that's exactly what Jamie said there. We take those neutrons out. So the control rods that are inserted into the reactor core, which the earliest designs of nuclear reactor didn't have, in those, the reaction rate was controlled by how long the fuel was exposed to neutrons from other fuel. That's what controlled the reaction rate. But modern reactors, they have control rods. Since the 1960s, they've had control rods. And the control rods are usually made out of what? Yes, gnome, exactly like wind scale. Yeah. Boron. Cadmium, you said it as you wrote it as I was saying it. Now, lead, I'm not sure about February spelt wrong. I don't think so, although it's an interesting thought. I wonder. There are radioactive isotopes of lead, and you wouldn't want to absorb a neutron and become radioactive. The advantage of boron is that when the boron nucleus absorbs a neutron, the product of that is still stable, so it doesn't undergo any sort of nuclear decay after that. So boron. So with the control rods, silver, possibly dvorak, yeah, possibly. So with the boron control rods, yes, I think you're right, Gnome, but that's for a particular type of reactor. I think it's for liquid salt reactors, but don't quote me on that. Yeah. So the control rods, you insert them in between the fuel and they absorb neutrons. As you retract them out of the core, you're absorbing fewer neutrons. That means there's more neutrons that can participate in nuclear fission and the reaction rate goes up. Lead-cooled fast reactor, yeah, that sounds right. Whereas if you insert the control rods, more neutrons are absorbed, and so there are fewer that can participate in super. Thanks for that, Gnome. There are fewer that can participate in nuclear fission, and therefore the reaction rate goes down. Now, everything else here is, well, almost everything else here is common to all other reactors that you get. Well, sorry, 1 second. Sigourney, what is it? I'm live to the nation. What's up? An Arctic bar. Can you reach them? Well, you have as much chocolate as you want. Okay. Don't break the fridge. Where was I? Oh, yes, I'm doing physics. Yes, so live to the nation. I can't remember what I was saying. Yeah, so everything in here, the nuclear part, there's one more thing, which is the containment structure, but not all nuclear reactors had containment structures. Wholesome moments with Keith. Eat all the chocolate you like. Anyway, so the containment structure made out of concrete, designed to keep gamma radiation in, yes, but that's what the biological shield inside the reactor here is for, not the containment structure itself. The main reason for the containment structure, yeah, I've made a video of that before, Jamie. No, the main reason for the containment structure is so that it can't be damaged by things coming in and hitting it, airplanes crashing into it, that sort of thing. I'll take your word for it. Nomi, you talking about Arctic bars, or I'm lost now. Anyway, so inside the reactor, then you've got something that gets hot and it heats up water. From there, yeah, the lead. Okay. From then on, everything's the same as every other power station. The hot water, I mean, this is a heat exchanger here. So the hot water in the primary core, let's get my cursor in the right place. Here's the primary core. The hot water in the primary core is up against the cold water in the steam generator here. They're not, the water can't cross that boundary. It's just a heat exchanger. Heating up this water, turning it to steam. Steam expands. It's under high pressure, which drives this turbine. But then that steam then gets cooled down by this condenser, which condenses that steam back into water, which gets pumped around again. That's the secondary circuit. Fair enough, Gnome. Don't worry about it. The turbine turns a generator, generating electrical energy, and the tertiary circuit here is used to in the condenser. There's another heat exchanger here, but the tertiary circuit's connected to a big reservoir or a river or a lake or the sea, and just gets cold water from there. Now it's very radioactive. So the hot water in the reactor vessel here is high-level nuclear waste. It has been in contact with the fuel. It has, it's been contaminated heavily. That has to be treated very, very carefully because it's incredibly dangerous. Yeah. So that's about the circuit in the condenser. Is that ever a loop? So to understand what you're talking about here. So you're saying, is this ever connected in a closed loop? Not that I'm aware of, Edward. No, it just goes to the sea. There are some clever things like if this goes to the sea and salt water is coming in, there has to be sacrificial components to prevent corrosion inside the pumps, that sort of thing. But in general, it's just going to the sea. No, yeah, I don't know. I'm fairly sure it is contaminated, but I could be wrong. Well, I mean, Chernobyl's a bad example because everything got contaminated in that case. In 𝗟𝗶𝗀𝗃 reactors, you have graphite channels, and then your control rods go into the channels, but there's still water that's used as a coolant. So gnome says it's in pipes between the fuel. That may well be the case. I'm afraid I don't know. That may well be the case. 𝗭𝘪𝘯𝘬𝘴 is absolutely correct. And there is an environmental impact of that. It does increase the temperature of the water by a few degrees. So there is an impact to that 𝗭𝘪𝘯𝘬𝘴. Yeah. Yeah, so the big difference between 𝗟𝗶𝗃 reactors and things like pressurized water reactors is that the moderator, rather than using water as a moderator, for example, it uses these channels of carbon. Yeah, and that sounds like a reasonable excuse to do it, Gnome. That certainly does, yeah. Yeah, and there are reactors, like the wind scale reactor, that used air as the coolant. They just blew air through the reactor core as the coolant. Which then, of course, that air going through the reactor core would then be contaminated. And if you go and look up the 𝗵𝗡 disaster, for example, I can't remember the name of the town. 𝗵𝗡 is the factory in the former USSR. There, where the Soviet government had built a factory to make plutonium, they didn't bother with the 3 circuits or anything. They just pumped water straight from the local river. That's the one, no, that's the one. Yep, the East Ural radioactive trace. They just pumped water straight through the reactor core and straight back out again and caused tremendous contamination. Right. So I think people are frantically typing away, which is wonderful. So before I move on into some more, what could go wrong? Yeah, they evacuated tens of thousands of people, but many of them far too late. Yeah. It's one of those things. I used to be very much pro-nuclear power. I saw it as the solution to many, many problems. But as I've got older, my opinions have rather shifted. What's the point of the moderator? Rather than having a turbine in a closed fuel loop. Particles not need slowing down, surely. Well, the particles do. The neutrons do need to be slowed down. And that's the point of the moderator. If you didn't slow them down, then you'd end up having a reactor that's harder to control. You'd have basically a bomb. Yeah, the water heats up. That's what it does. So, Edward, when I say the water molecules speed up, that means the kinetic energy of the molecules has increased, which means the temperature of the water has gone up, which is why in a pressurized water reactor, we use the same medium for moderator as we do coolant. water. In advanced gas-cooled reactors, they use CO2, for example, as the coolant, and they have to have a separate moderator. And it's even more tricky than that, because water, really good moderator, it does also absorb neutrons, but not at the same rate that it slows them down. Carbon absorbs neutrons, but it does also slow them down, but not at the same rate. So, you know, you've got to be careful in the reactor design, because things don't just do one thing. I'm afraid I don't think I understand what you're saying, Edward. Rather than speeding up the water, again, by speed up the water, I mean increase the temperature of the water, keep the turbine with the uranium. I don't understand what you've said there. It's coming up very soon, Jammy, very soon. I just want to try and get to grips with what Edward's saying. Yeah, still very much GCSE at the moment. So, Edward, if I understand what you're saying, it's why not have the generator or the turbine connected to the primary circuit? And if that's what you're saying, then maintenance of the equipment is going to be far more challenging, because it'll be contaminated. So in order to safely maintain the moving parts that need to be maintained, we keep them outside, we keep them separate. So I think, if I've understood your question, I think that's there. There is one last bit of GCSE. It's not a big bit. It's one equation. It's this equation. It's gone off the edge of the screen. Yeah, no worries, Edward. 1 second, it's gone off the edge of the screen. That equation there, the world's most famous physics equation, E equals mc squared. It's not an equation you need to remember at GCSE. And yet, you need to know that there's an equivalence between mass and energy. They are not equal, but there is an equivalence. And the reason why all this works is that when a nuclear fission reaction takes place, mass vanishes. And energy is created. So it's not true that energy is never created or destroyed. It's not true that mass is never created or destroyed. There is an equivalence. Now, I know, yeah, mass becomes energy. Now, I know that that statement is riddled. Well, it's not quite that way, 𝗏𝘬𝘶. There's a subtlety to this. I'm still teaching that mass and energy are somehow different, and we're converting from one to the other. The picture is deeper than that. And if you look up sort of momentum stress, I think it's momentum stress tensors, energy stress tensors, that sort of thing, you can see that it goes a lot more complicated than that. Yeah. Yeah, mass, well, what is mass is a deep fundamental question. And what is energy? These are fundamental questions that I'm not answering, because the answer is too complicated. It needs general relativity. I can't remember it. I studied it 18 years ago. I studied general relativity. I don't remember it. So Noma says mass is an energy store. That's fine. That is fine as a model to understand what's going on here. But it's not quite the full story. Okay, so just bear that in mind, that what we're talking about here is not the full story. But for GCSE physics, as a model to understand what's happening, mass is destroyed, energy is created. Jammy's correct. Energy is E, capital E. C is the speed of light. Absolutely right. Is general relativity a university near? Pranav, it depends on what university you go to. I have a colleague who I shan't name. I won't even name what school he goes to. But I have a colleague who did not study general relativity as part of their physics degree. And they are a qualified physics teacher with a physics degree. I did do general relativity. All physicists will do special relativity, but they don't always do general relativity. Yes, Sly, absolutely yes it can. And when you study A-level physics, when you study A-level physics, you will see how elegant and beautiful this model that we are presenting to you, special relativity, how elegant and beautiful it is. But it's not the full story, and just remember that. So, let us now get cracking with some A-level. Hey, if you're GCSE, I encourage you to stick around, but you don't have to. You didn't have to do anything. Hello, quantum gravity. You don't have to do any of this. This is all optional. But if you're an A-level student, this is where it gets fun for you. Hello, 𝗟𝘂𝗲. Yes, hello. I didn't want to use your real name in case you didn't want it known. Yeah, Pranav's absolutely right. So, here we go. Hopefully you can see that table of teeny tiny numbers. If you can't see the table of teeny tiny numbers, then I have pinned a post in the Discord channel with the spreadsheet from which I pulled these numbers. These teeny tiny numbers. Au revoir, Jammy. So, what are we looking at with these numbers? We are looking at... Here's a file. Here it is. Thank you. Thank you very much, Helicopter Boy. So we are looking at some basic data here. A-level students, U, the Unified Atomic Mass Unit, 1/12 of the mass of a carbon-12 atom is 1 U. It's a unit of mass. This is the mass of a proton, neutron, electron in unified atomic mass units. This is what 1 unified atomic mass unit is equal to in kilograms, to 3 significant figures. An electron volt to 3 significant figures in joules, and the speed of light to 3 significant figures in meters per second. Right, now what's about this table? Z, you tell me. What's Z? A-level students, well... Charge, sure. Proton number. I prefer proton number. James isn't incorrect. Proton number or even atomic number of an isotope. Yeah, I knew what you meant, Gnome. That's okay. Wombat, you've got it. Atomic number. Next to it is the chemical symbol. Then we've got A. What do you think A is? The mass number, the atomic mass, that's right. And lastly, we've got this column that says mass of the atom in unified atomic mass units. The mass of the atom. And so what we're going to do is we are going to work through a few different problems. We're going to work through a few nuclear physics fission reactions to calculate the energy that's released in a fission reaction. And that's what I want to spend the last 15 minutes doing. It's good to practice this sort of thing. So I'll leave that table there. And what I will do is I will give you a reaction. And then I will want you to calculate how much energy is released. And the way you do that, I'll explain. But if you know how to do that, you can get cracking. So here's what we're going to have. We are going to start with uranium 235. I hope that's visible. 92. And we are going to add to that a single neutron, which is absorbed by the uranium-235 nucleus. That is going to undergo fission, and it's going to become Ce. Now, I can't remember. I don't think that's cesium. What is Ce? Anyone remember? I'm not a chemist. Cerium. Right, thank you very much. 58 for cerium. Plus, we're going to get Zr. Is that zirconium? Something like that. 91. And, of course, we're going to get, yeah, zirconium. We're going to get 3 neutrons emitted as well. So all I want to know, how much energy do I get out of that reaction? So if you know how, you can put your fingers in your ears and just start working on it. If you don't know how, this is what you need to do. Calculate the binding energy of this nucleus. Calculate the binding energy of this nucleus and the binding energy. Yeah, should be. You're quite right, helicopter. No, I'm right. No, I'm absolutely right, helicopter boy. No, I'm correct. I'll see if you can figure out why. So, calculate the binding energy of this nucleus, the binding energy of this nucleus, the binding energy of this nucleus. Okay? So the binding energy of this nucleus is how much energy I'd have to put in to separate it out into all its nucleons. The binding energy of this nucleus is how much energy I get out when this nucleus forms. The binding energy of this nucleus is how much energy I get out when this nucleus forms. And the difference between the total binding energy on the right and the total binding energy on the left, well, that's the energy that's released. We can assume that electrons, well, they don't contribute to binding energy really anyway, so ignore them. I suppose I better work out the answer myself. Oh, no, I didn't think of that. You lot are going to be faster than me because you're younger. Oh, slow down, I'm doing it. Cerium. Zirconium. Where's zirconium on my table? There you are. There's zirconium. Zirconium 91. And then so, Gnome has got a number which looks very similar to mine, but not exactly the same. And it's probably because I've chosen a slightly different way to do this. I think your answer is correct, Gnome. I think your answer is correct. And when you see how I've done it, you'll see what the effect is of these what we call rounding errors. Using these numbers to 3 significant figures. Yeah, actually, I did 2. Not that, though. 931.3 is what I used. Yeah, I used 931.3. So, if I've recalled that number incorrectly, because it was off the top of my head, then I'm happy to be corrected. Fascinating. Stand by. So, interestingly, your data booklet appears to have changed. So if your data book says 931.5, I happen to know, Wombat, which data booklet you're talking about, and I know that a legacy version of the same document has 931.3 megaelectron volts. Isn't that interesting? So here's what I did. And if you did something different, then fine. There's different ways of doing this. Yeah, fair enough. So it's more likely that the legacy one was wrong and the new one is right than the other way around, let's be honest. Oopsie, don't want to look at that one yet. That's for later. 1 second. You can minimize. There we go. Yeah, you've messed up somewhere there, Pranav. Oh no, hang on. Did you edit your answer? Because your answer now looks different to what it looked like before. Yeah. So here's what I did. I first of all wrote down that uranium-235 had a mass of 235.043, and all of these numbers are going to be in unified mass units. Unified atomic mass units, that's U. And I added that on the left-hand side to the mass of a neutron, which I gave here like this, but it could well be different to what it says on your data sheet. Anyone know why, by the way, these numbers might be slightly different? There are reasons. Apart from the possibility of a typo on a legacy sheet for 931.5, and if you're interested, those of you who happen to know what school I'm in, feel free to pop over to SF12 at some point, my classroom, and I'll show you the legacy sheet with it different on it. Anyway, so I did that. Anyone know why the numbers will be slightly different? Well, Pranav, it really doesn't. It really doesn't matter, because the binding energy of the electrons is not a nuclear binding energy, but the binding energy of the electrons is tiny, absolutely tiny. You know, we're talking in the order of 200 million electron volts, and to ionize an atom, you're talking about 10 electron volts. So it's completely, you know, different scales here. Not quite Wombat. Yeah, partly. But part of the reason why it's so difficult to pin down what the number is because the number is not a fixed number. It's a probability. Temperature shouldn't matter, Wombat, because we're talking about the mass of a neutron. So temperature, well, I suppose it would. If the neutron's moving faster, it will have more mass. Or would it? It wouldn't. That's one of the mistakes of special relativity. Anyway, I've got distracted by my own thoughts. No, the masses aren't actually fixed. So they're all distributions of what the mass probably is around about. So I've got the mass before the fission of being that. The mass after the fission, I can now calculate. So that is the mass of my cerium-142, which is 141.909 U. I can add that to the mass of my zirconium, and that's zirconium-91, which is 90.905 U. And I can add that to 3 lots of neutrons. And if I do all of that, I get a number. And I'm just going to work out what that is because I cleared my calculator because I'm a moron. 905, and then 3 lots of 1.00867. Okay, so you end up with 235.840 atomic mass units. Now, the difference between those two is the mass defect. Actually, I shouldn't say that, but it is. I shouldn't say mass defect. I'm going to say the mass difference. The mass defect refers to a single nucleus. It's the mass difference. It's the mass that's vanished. It's the mass that no longer exists that used to. And because I use reverse Polish notation on my calculator, I just press subtract and I've got that answer straight away. So I now have a mass difference, and I'm going to use delta M, not to mean mass defect, but to mean mass difference. The mass that's vanished of 0.211660 unified atomic mass units. Okay, great. Now what? Well, at this point, you could convert that into kilograms and use E=mc², and then convert the answer into megaelectron-volts afterwards. Seems like a lot of work. Or you can use that lovely little equivalency that you get in your A levels with somehow debatable numbers, which is 1U is equivalent to, don't use an equals, it's incorrect, is equivalent to 931.5 is what you've got, mega electron volts. Well, that's what 1U equals. What does 0.211660 U's equal? So 931.5 multiply, and that gives me my final answer, which I think is in agreement with what everyone else here wrote. So let's just 0.211660 multiplied by 931.5 equals 197.161, and that's in mega electron volts. That is a lot of energy. When you consider that 13.6 electron volts is the ionization energy of hydrogen, that's a lot of energy that's released in this particular reaction. Right, we could pick some more reactions, but that one took a bit longer than I expected to. Don't worry, I've set you an Isaac Physics task, as I do. Some of you may, of course, have already done these, but if you haven't, it's all good to do. So if you go to the link below, if you're not already, I'm about to post it into Discord. Let's go ahead, click that link. Go to Isaac Physics, join that group, and I have set a homework task. Here it is. It starts with some GCSE questions. You might be talking to the wrong person there, Helicopter Boy. Might be talking to the wrong person, I think. Yes, it starts with GCSE level. If you're an A-level student, try it out. Do it. You might think, oh, it's far too easy. It's far too basic. Why should I bother? But that would be the wrong attitude. Physics is good fun, whether it's easy or hard. Okay, and then it moves on to A-level. Year 12s, you probably haven't seen J4 before. Year 13s, depends on what school you're in. My year 13s have seen J4 and probably have frequent nightmares about it. Yeah, exactly, Helicopter Boy. So J4, it's a very, very important one to do. So have a good crack at that. If you've done all of that and you want some more, well, do you know what? You've got that spreadsheet that I put on the pinned post on this. You know the proportion of the daughters here, the fission products. You know what they are. Pick some. Try it out. Do some calculations yourself. Try it different ways. Don't just use the 1U is equivalent to 931.5 mega electron volts conversion. Try using E=mc² and converting the mass into kilograms and the energy back into mega electron volts. Try these things. It's always good to do. The last thing I want to show you, because, you know, I want to. Here it is, the schedule. Now, if you've never tuned in to Physics with Keith before, you may not realise that there is a schedule. This all comes impeccably planned. But here we are, physicswithkeith.com. It's up for renewal in November. I have to pay again. But if we scroll down, you'll see that there is nuclear energy. That's the one we've just done. And then below that, Kirchhoff's laws. That's where we're going. So next week, you click that link, and you'll go to next week's video, a live broadcast, and so on and so on and so on. Isn't that wonderful? Someone's thought this through. I did have a little simulation loaded up from the National Physical Laboratory to show you where we could split nuclei and see what comes out. But, you know, I'm out of time. It's now 7 o'clock. So I guess that'll have to wait. Right, I really hope that has been useful. If you have not already subscribed, then can I encourage you to do so? It helps me out. I'm over 2/3 of the way to being able to embed my live stream into my website. So if you're not subscribed, please do so. Share this with your friends. You might have found it useful. You might not have found it useful. But maybe you'll find next week useful. Do share it with your friends. Make sure that as many people as possible are getting the benefit. Yeah, you'd think that would be the right sort of thing for me, Edward. Yeah. Should be head of physics or something, shouldn't I? One of the top grammar schools in the country. Anyway, look, it's 7 o'clock. My daughter wants me to play with her, which is what I want to do. So I'm going to go. Thank you very much. I'll see you next week. Take care of yourselves.